Every time a fridge is opened, it releases gases that trap heat up to 4,000 times more effectively than carbon dioxide. These refrigerant gases quietly leak from millions of cooling systems around the world, fueling an environmental disaster that rarely gets attention. But scientists may have found a solution, making things cold using nothing but magnets. No harmful gases, no leaks, and no greenhouse effect. This breakthrough has the potential to replace many of today's cooling systems. Here is how magnetic cooling actually works, and why it might help save the climate. First, it's important to understand why current cooling technology is so problematic. Most people worry about car emissions, but there's an even bigger climate threat quietly running in nearly every kitchen. That humming refrigerator contains chemicals that make carbon dioxide look harmless by comparison. These refrigerant gases leak from cooling systems across the globe, causing serious environmental damage that often goes unnoticed. Home air conditioners, for instance, leak refrigerant every single year. Households typically lose around 5% of their refrigerant annually, while larger systems like those in supermarkets lose even more. In climate terms, that's equivalent to thousands of gallons of gasoline. These leaks are invisible, odorless, and easy to ignore, but when multiplied across millions of homes and businesses, their impact becomes enormous. Commercial systems can lose substantial amounts of refrigerant each year, sometimes with a climate effect comparable to burning massive quantities of fuel. Within the refrigeration industry, this is labeled as normal operating loss, but there's nothing normal about routinely releasing super-potent greenhouse gases into the atmosphere. What makes these gases so dangerous is their potency. Hydrofluorocarbons, the most common refrigerants in use today, trap heat in the atmosphere between 1,400 and 4,000 times more effectively than carbon dioxide. To put that in perspective, releasing just 1 pound of refrigerant gas has the same warming effect as burning 2,000 pounds of coal. A small leak in a home air conditioner can have the same climate impact as idling a car for a month on end. Traditional cooling systems rely on a gas-based cycle. The refrigerant is compressed to become hot, then expanded to become cold. This hot-cold loop moves heat from the inside of the fridge or building to the surrounding air. It only works because these gases can shift between liquid and gas states at very specific temperatures. Every modern cooling system depends on this principle, from household fridges and air conditioners to car AC units and industrial freezers. Without these chemical refrigerants, the entire process grinds to a halt. The challenge is growing rapidly as global demand for cooling surges. Air conditioner sales are rising year after year, especially in countries like India and China, where economic growth and rising temperatures are driving installation of millions of new units. That means more refrigerant in circulation, more leaks, and more climate impact. Industrial applications add even more pressure. Cold storage warehouses use thousands of pounds of refrigerant to preserve food during transport. Data centers rely on massive cooling infrastructure to prevent servers from overheating. These systems often contain huge volumes of harmful gases, amplifying the risk. Here is the troubling paradox. The world needs more cooling because of climate change, but cooling systems are making climate change worse. Heat waves increase demand for air conditioning, which boosts both refrigerant leakage and electricity use. AC units also dump waste heat into urban environments, contributing to the heat island effect. This creates a vicious cycle. More heat drives more cooling, which generates more emissions. The refrigeration industry has attempted to solve this by developing better gases. Older chemicals like CFCs were banned for destroying the ozone layer. Their replacements, HFCs, don't affect ozone but trap huge amounts of heat. The latest alternatives tend to be expensive, flammable, toxic, or incompatible with existing equipment, posing new safety and logistical challenges. Leak repair is another part of the problem. When an air conditioner starts losing performance, many people simply add more refrigerant instead of addressing the leak. It's a cheaper, short-term fix, but it guarantees that more gas will escape over time. Proper leak detection and repair can cost hundreds of dollars, which means many small leaks go unrepaired. Even when cooling systems work properly, they eventually reach the end of their lifespan. All refrigerators, air conditioners, and commercial units often contain several pounds of refrigerant. Unless they're carefully dismantled using specialized tools, those gases can be released during disposal. Unfortunately, many scrap yards and waste haulers lack the training or equipment for safe recovery. The impact is staggering. Refrigerant gases currently account for roughly 11% of global greenhouse gas emissions, more than the entire aviation sector. If the current gas-based approach continues, emissions from refrigerants could grow by 500% by 2050. Clearly, a different path is needed. Simply switching from one chemical to another doesn't solve the underlying problem. That's why researchers are now focused on a completely different strategy, one that eliminates gases altogether and turns the entire concept of cooling on its head. Scientists have discovered that certain materials can heat up or cool down when exposed to a magnetic field, a strange but powerful effect that could one day replace many of today's cooling systems. This phenomenon works completely differently from conventional refrigeration. There's no gas compression, no chemical refrigerants, and no moving parts prone to wear and tear. Known as the magnetocaloric effect, this isn't science fiction. It's a form of physics unfolding at the atomic level. Inside certain materials like gadolinium, there are countless atomic compass needles, tiny spins that point in random directions under normal conditions. Here's where the transformation begins. When a strong magnet is brought near gadolinium, all of those atomic spins suddenly snap into alignment. Much like iron filings lining up around a magnet, this alignment process releases energy as heat, causing the material to warm up. Then comes the cooling. Once the magnetic field is removed, those spins lose their alignment and scatter randomly again. This return to disorder absorbs energy from the surrounding area, cooling the material. The shift happens instantly, every time the magnetic field changes. In practical systems, engineers harness the cycle to create continuous temperature control. One example is a setup developed at Ames National Laboratory. It uses a rotating disk of permanent magnets that pass over multiple beds of magnetocaloric material. As each magnet approaches, the material heats up. As it moves away, the material cools. This rhythmic cycle repeats hundreds of times per minute. Water with corrosion inhibitors circulates through the system, absorbing heat from the worn material and releasing it elsewhere. It then flows back to repeat the process. The result is a cooling effect similar to traditional systems, but achieved without any chemical refrigerants. The simplicity of magnetic cooling is part of its appeal. There are no compressors to break down, no refrigerant gases to leak, no intricate chemical balancing acts, and the system uses solid materials, permanent magnets, and water-based fluids to move heat efficiently and safely. This method addresses every major weakness of traditional gas-based systems. Another bonus, magnetic cooling systems run almost silently. Conventional units generate noise from compressor motors, fans, and a flowing refrigerant. Magnetic systems, by contrast, produce only soft sounds from water pumps and rotating magnets, making them ideal for quiet environments like bedrooms or libraries. Efficiency is another advantage. Traditional systems waste energy in compression, expansion, and multi-step heat exchanges. Magnetic systems convert magnetic energy directly into thermal changes, with fewer losses along the way. This streamlined process ensures more of the input energy goes toward actual cooling. Field strength can also be adjusted to fine-tune the cooling output, a feature still in development. While gas-based systems switch on and off to maintain temperature, magnetic cooling could offer smoother control by varying the magnetic field or rotation speed. The environmental upside goes beyond eliminating refrigerant emissions. Magnetic cooling uses materials like gadolinium, which is widely available and recyclable. The magnets retain their strength indefinitely. Even the fluid circulating through the system is water-based and environmentally safe. Working prototypes already exist, and they've shown they can reach refrigerator-level temperatures using only magnets and magnetocaloric materials. These systems have performed consistently across thousands of heating and cooling cycles, with no loss in material performance over time. The technology is scalable, from small portable coolers to large commercial refrigeration systems. Researchers are currently exploring new materials that outperform gadolinium, either by achieving greater temperature swings or requiring weaker magnetic fields to function. So who's actually turning this into real-world products? Let's look at the companies bringing magnetic cooling to the market. Several companies have already advanced beyond prototypes and now offer working magnetic cooling systems. A German firm called Magnum, for instance, sells a commercial magnetic cooler called the Polaris unit for around $7,000. This isn't a futuristic concept or a lab-bound prototype. Real businesses can already purchase magnetic cooling systems that eliminate refrigerant gases entirely. One of the most sophisticated designs comes from Ames National Laboratory in Iowa. Their system features 9 beds filled with gadolinium particles arranged in a circular formation. A spinning disc embedded with high-powered magnets rotates over these beds, triggering continuous heating and cooling cycles. Water circulates through the system, carrying heat away, similar to how coolant works in a car engine. European companies are already applying this technology to real-world businesses. At a major trade show, Magnetocaloric demonstrated its working magnetic refrigerator by serving cold drinks to curious visitors. Their target markets include supermarkets, hospitals, and data centers, places that run cooling systems continuously and are highly sensitive to energy costs. Even modest improvements in efficiency can translate into thousands of dollars in savings for these operations. Magnetocaloric has progressed to what it calls the pre-industrial stage, building systems that generate over 6 kilowatts of cooling power, enough to keep a walk-in restaurant freezer at proper temperature. However, magnetic cooling still faces significant challenges. To operate, these systems require magnetic fields stronger than 1 Tesla, which calls for powerful permanent magnets made from rare earth materials. These same materials are also used in electric vehicles and wind turbines, creating high demand and tight supply, factors that drive up cost and limit availability. With commercial units already in use and research underway to overcome technical hurdles, the key question now is whether magnetic cooling can make the leap into households. If it can, it may radically change how society keeps things cold without heating up the planet. Bringing magnetic cooling into everyday homes means tackling some significant hurdles. Research teams are already working to make these systems more affordable and compact for residential use. At Ames Lab, scientists are testing new materials that could dramatically reduce costs while shrinking the size of magnetic cooling units to fit inside a standard kitchen. If material prices drop and designs continue to improve, experts believe consumer-ready systems could arrive within 5 to 10 years. Magnet costs and bulky system designs remain real obstacles, but research into new alloys like those being explored at Ames Lab shows promising progress. Imagine every air conditioner and refrigerator on the planet switching to magnetic cooling. Such a shift could prevent billions of tons of greenhouse gas emissions from entering the atmosphere. If you found this tech breakdown useful, share which application you think magnetic cooling will disrupt first in the comments.